Okay, so we are recording. The last class, and you have this example copied down in your notes. Just go to your notes. In this problem, we were being introduced to triple integrals, section 12.7, and I was trying to justify a reason to you why we would use a triple integral. And one reason is to find the center of mass for a solid in three-dimensional space. So in this problem, let's review what you've done so far, what you've copied so far. You have a solid that's bounded by the parabolic cylinder x equals y squared. So that's a parabola graphed along x equals y squared, but it goes up and down forever. Okay, a vertical. So a parabola being that it's a parabola that the z value can be anything. So think of stacking a bunch of parabolas, x equals y squared parabolas on top of each other at different heights. That'll generate what's called this parabolic cylinder. Now, the parabolic cylinder, though, to be a solid of finite volume, well, a solid of, if you want to find a centroid, you need a finite solid, right? So you have to have a plane planes or other surfaces that bound this. So the parabolic cylinder goes up and down forever, but it's bounded above by the plane z equals x. It's bounded below by the xy plane given by z equals 0. And then it's bounded in the front by the vertical plane x equals 1. And we're assuming constant density. So recall that this was a picture of our solid. Okay, you see it's bounded in the front by the plane x equals 1. That's this plane here. Bounded on top by the plane z equals x. The parabolic cylinder bounds it on the sides. And then you're bounded below by the xy plane. And so remember what we had to do. We had to use a triple integral to, since density equals mass over volume, then mass is density times volume. And so the way we compute the mass would be then this triple integral that you see here. And we're going to use Cartesian or rectangular coordinates. And how do we get the limits? Well, let's remember the z limits come from going from a surface on the bottom to a surface on the top. So the bottom surface, okay, that's why I drew this red line here. It goes from a surface on the bottom, which is the xy plane, to a surface on the top, which is the plane z equals x. So therefore, z equals 0 is your bottom surface, and z equals x is your top surface. And those are your z limits. But after you get your z limits, okay, you need then to establish your region D in the xy plane. Well, if you project this solid down into the xy plane, it's going to trace out this parabola, and that creates your region D. And you've worked some on section 12.7. You had an assignment on that due today. So you have some experience with this. So the x limits are, for that region D in the xy plane are x equals y squared and x equals 1. And then y goes from 1 to negative 1. Okay, so we computed this mass. And we use iteration when we do our triple integral, just like a double integral, we use iteration. And the mass turns out, after we went through the steps, and we have a constant density, rho. Okay, now that rho, by the way, doesn't have anything to do with the rho in spherical coordinates. It just stands for constant density. We ended up getting a constant density of 4 rho over 5. 4 rho over 5. and I'm sorry, we got a mass. The mass was equal to 4 rho divided by 5. And now what we want to do, is we want to find the centroid, or the center of mass. So we need the formulas that will help us get the center of mass. And the formulas are very similar to their counterparts to the formulas that you learned for the center of mass for a lamina. So now here's where I think we're starting fresh. So first of all, we have to take the moments and divide them by the masses, or I'm sorry, the moments and divide by the mass to get the centroid. But in this case, the moments are going to be not about axes, as was the case with the center of mass for a lamina or a plate. Here, the moments are about XY planes. And sometimes you don't need to do computation to get your moments about the planes. So for instance, the moment about the XC plane is equal to 0. And that's because the mass, this mass of constant density, okay, will balance perfectly along the XC plane. I'll go back to this page, but if you look at the picture, here, okay, that solid there, which looks like the front of a vacuum cleaner, right? That solid balances perfectly along the XC plane. Okay, the XC plane defined by the X and Z axis, that solid with respect to that XC plane balances perfectly. The XC plane cuts that solid. Okay, I mean, if you were to cut that solid with the XC plane, the cut would be right here, right? That's where the cut would be, and it would split that solid exactly into symmetric halves. And since the density is constant, well, the solid would balance right along that XC plane perfectly. And so therefore, the moment about the XC plane is 0. Okay, does that make sense? In other words, hold on here. The moment, let me try to make this a little nicer. Hold on. Let me just do this again here. The moment about the XC plane is equal to 0. Okay, are there any, I mean, does that make sense? Who's feeling comfortable with that? Okay, Charles is good, Ellie's good, Malik and Juliana, excellent. And Ian, wonderful. Actually, okay, many of you, okay. Well, now let me ask you this: with respect to the YZ plane, okay, does this solid balance perfectly along the YZ plane? Charles says no. Okay. That's right, the YZ plane. That's right. In other words, the YZ plane, right? The YZ plane goes, if we were to continue the axis, hold on, let me just, there it goes. Is this solid with respect to the YZ plane, Is any of the solid like on the other side of the YZ plane where the x-axis is negative? No. So therefore, the solid, it's all in front of the YZ plane. So it's not balanced at all along the YZ plane. Not at all, right? So we can't use symmetry to get that moment. So let's go then to the moment about the YZ plane. So the moment about the YZ plane, of course, in front of the density and your, you have your dV here. You're going to put an x because x is the distance from the YZ plane. So again, this is a counterpart to the moments about the x and y axes that you learned for when you did center of mass or found center of mass about a lamina. And the limits don't change. That's kind of nice, right? The limits don't change. The solid's still the same. These limits, limits here are the same limits that we used when we found the mass. And you could work it out, and it'll turn out that the moment about the YZ plane is 4 rho over 7. Now, similarly, the moment about the XY plane is also, let me just go back here. I'll go back to that page, but if we look at the XY plane, right, the XY plane, okay, and if I draw like a, hold on, that isn't what I want. Yeah, it is actually. The XY plane, the whole solid, right, is above the XY plane. None of it's below. There's no, I mean, we have to compute the moment about the XY plane. We can't use any symmetry to help us. And this solid is not a symmetric kind of solid. It's not like a cube or something of constant density. I mean, the density we're working with is constant in this case, but the solid is not like, there's no symmetry really in regards to that solid. I mean, in of itself. So we need to find then the moment about the XY plane, and of course, moment about the XY plane, you're going to have a z then inserted in before the density. Because what determines the moment about the XY plane? How far the points in the solid are from the XY plane, and that's a z value, right? And so, you get 2 rho, you'll get 2 rho over 7. Okay, are there any questions so far? So you see, we need the triple integrals to do the center of mass for this particular solid. Now we're not done yet, but we need the triple integrals to get the moments about the XY planes. And I note here that yes, we are using constant density, but that density function, right, could be a function of x, y, and z as well. Okay, let me see. There was a question here. Okay, Juliana's feeling good. All right. All right. I'll go to the next page then. Are there any questions? Okay. So the center of mass then is defined. The x bar is the moment about the YZ plane over the mass. Y bar is the moment about the XZ plane over the mass. And the Z bar is the moment about the XY plane over the mass. Okay, so again, it's analogous to what you've seen with center of mass, a definition of a center of mass or centroid for a plate or a lamina. Okay, and so you just work out the math here, and the densities simplify out, right? And then you get a concrete point, which is the center of mass. It's a 5/7, 0, and 5/14. Now, a question we can ask is, does this seem reasonable based on the picture? And this is one reason why it's kind of nice to do problems where you have constant density, because it allows you to more easily check for reasonableness. It doesn't mean you can't do it for a density that is variable, but you know, if the density function is too complicated, it's kind of difficult to intuitively say, yeah, this my centroid, my center of mass makes sense. It's kind of hard, you know. So I note that 5/7 is greater than 1. Okay, so X bar is greater than 1, and Z bar is less than 1. Okay. Oh, hold on. I got a typo here. Hold on. Yes, hold on. That's not what I want. Thank you, Ian. One moment. Let me. I meant a half. I meant a half, and let me fix that in my notes as well. So here, I mean a half. Thank you. Thank you. Okay, so let's remember what the center of mass is. The center of mass is the exact point where an object can be perfectly balanced, sometimes called the center of gravity. So we notice that, for instance, that X bar, okay, is greater than a half. Let me go back to the picture here. Let's see why that would make sense. Okay, and I'll come back to that page, but you know, here's the picture. So 1/2 is right here, right? 1/2's right there. And they're saying that the X bar, in regards to the center of mass, is equal to 5/7. 5/7 is about 0.71. Okay, so the hold on here. Here is like where the X bar is. Okay, there's like, so why would the X bar, okay, which is you know, 5/7, why would it be past the 1/2 value? X equals a half. Why would the 5/7 be, why would X bar be greater than 1/2? That's what I'm trying to say. Based on the solid. Well, if you look at the YZ plane, and I mean, I guess what I'm saying is, why isn't X bar equal to a half? I mean, you know, in regards to the solid, okay, you know, like here's the halfway point, right? Is the solid heavier in front of the halfway point on the x-axis, or is it like if you compare how quote heavy the solid is in regards to moving along the x-axis, it's heavier in front of x equals a half. So like along the x-axis, that's right in. When x equals a half, okay, if you look at the solid in front of x equals a half, and look at the solid between the origin and x equals a half, would you agree that the solid's heavier in front of the point x equals a half? Who agrees with that? Maybe give me a thumbs up. Okay, Kino agrees with that. Ian, Gordon, Ellie, excellent, excellent, excellent. Madeline, and so that's going to move your X bar then to be greater than a half. Charles agrees. Now, what about Z bar? What about, so that's why, you know, X bar is equal to 5/7. What about, while we're at it here, what about Z bar? We know Y bar equals 0, but what about Z bar? Well, okay, let me just see here. Hold on. So I can draw a line right there, little line segment, and that corresponds to Z equals a half. So in terms of the plane, I guess I could call it the plane, Z equals a half. Is the mass heavier above the plane Z equals a half, or heavier below the plane Z equals a half? The horizontal plane Z equals a half. That's right, Ellie. It's heavier below. Okay, so just like with respect to X bar, the solid with respect to the X bar, the solid was heavier in front of the plane X equals a half. That caused X bar to be greater than a half. In this case, the solid with respect to the vertical direction, the solid is heavier below the plane Z equals a half, and therefore that's going to move the Z bar portion of that coordinate. It's going to move it below the plane Z equals a half, and that's why you have a Z bar of 5/14, and 5/14 is actually 0.357. So was this helpful, this little discussion? Was this helpful? How many are feeling? How many are feeling good? All right, thank you, Ellie. All right, excellent, Gordon. Thank you. Excellent, Juliana. Thank you. Okay, Ian, wonderful. So, you know, you're going to have some problems in your homework dealing with center of mass. And certainly, you know, on the exam, you could see problems. And, you know, it's nice to be able to check if your answers are reasonable. And again, you know, for the one answer there, the 0, that was just, you know, we didn't even need to do any work to figure out that y bar would be 0. Okay, if we're good on this, I'll move to the next example. Are there any questions? Okay. All right, this example here is not necessarily one to copy. This is like a little exercise that we're gonna do together. You're gonna see it in your homework as well. Okay. So let's talk about this. Okay. So what they've done here is you have a region of integration for this integral. Okay, and what they're doing in this example is you know, you have dz, dy, dx. So dz means you are going, your first limits with respect to z here go from a surface on top, or no, a surface on the bottom to a surface on top. Let's see, maybe I can do it like this. Kind of like, yeah, like that. Well, I want to kind of have it show. I want to have it show good. I want to have it show well. Let's try it again. No. Come on, don't give me that. Okay. So the surface on the bottom is a function of x and y, right? The surface on the bottom is a function of x and y. What is the surface on the bottom? Based on the figure here. What is the surface on the bottom? It's a plane, right? The xy plane. That's right, Yunus. So that's z equals 0, right? And then the solid goes all the way up to, it goes up till it hits this top plane. What's the equation of the top plane? Z equals 1 minus y. That's right, Ellie. And so here is your top surface. Okay, and now what you do, right, is you take this solid and collapse it down into the xy plane, and that's going to give you then, that's going to give you your region D. So I don't know, this thing, it never works right. Let's try to do it right. Hold on. Okay, so here's the x, y plane. And you see that if you projected that solid down into the xy plane, region D would look like this, right? That would be your region D. Bounded below by the function y equals square root of x, and bounded above by the line y equals 1. And that's how you get then these next two limits. Okay, bottom function, top function. And then the x limits are going to go from 0 to 1, obviously, because y equals 1 meets y equals square root of x. Those functions intersect at the origin and 1, 1. So this exercise is not designed to test your ability to compute integrals. It's designed to test your ability to find the right limits. Are there any questions so far on what I've showed you here? All right. Well, what we want to do is we want to rewrite this integral as an equivalent integral in the 5 other orders. 5 other orders. Okay, so for instance, what would one of those orders be? Well, let's say, what's probably the easiest one to do? What's the easiest one to do? So, right, you got dz, dy, dx. You have dz, dx, dy. You have dx, dz, dy. You have dx, dy, dz. And you have dy. Hold on here. Hold on. Well, this one we already did, right? We did that. I mean, they gave us that one here. You have dy, dx, dz, and you have dy, dz, dx. Okay? So, of the, 1, 2, 3, 4, 5, 6 orders, what's going to be the next one you should probably do? And one we already have, right? So order 2, 3, 4, 5, or 6, which is the easiest? Well, okay, Emma thinks 6 is. Let's see what you think. Okay, we need you to volunteer here, volunteer some answers. Think about it for a moment. I need more than Emma. I mean, I want Emma, but I want you all to throw out some answers here. Okay, Ellie thinks 2. Think a little bit. Hang on here. Hold on. There was a. So what I'm saying is, we have 6 different orders of integration here. You have dz, dy, dx. Okay. you have, hold on. Let me show you here. All right, so, okay. So, you have dz, dy, dx. You have dz, dx, dy. You have dx, dy, dz. You have dx, dz, dy. You have dy, dx, dz. You have dy, dz, dx. Now, dz, dy, dx is the first order of integration that they did, and they have all the limits here for if you're going to integrate with respect to z first, y second, and x third. Here's what the triple integral is going to look like. What they're asking here is they want you to find the 5 other integrals for the 5 other triple integrals for the other orders. And what I'm asking is, of these 5 remaining choices, which choice would be the easiest one to do? Choice 2, 3, 4, 5, or 6. And I'm going to give the answer in a moment here. I know nobody's working on the homework because I've deactivated it. So if you're so let's all offer an answer here. It helps to participate, right? Even if you're wrong, it helps to participate. If you don't answer, you're wrong. Okay. Okay. A lot of people are saying 6. Okay. Malik's saying 2. Ellie says 2. Okay. Thank you everybody for participating. Kino says 6. Well, I'll tell you. At least in Marwan says 2. Thank you everybody for participating. I think everybody's answered. Or most everybody. The answer, in my view, is going to be order 2. Because we already have dz first here, right? We already have dz first. So for instance, if I do okay, hold on here. I got to make this a little bit. One moment. If I do dz, dx, dy, well, my z limits are 0 to 1 minus y, right, from up here. So I don't need to do those. I can just copy those. Right? But now we need our x and y limits. Well, the region D is still going to be this region here. It's still going to be this region. Try to make this look good. Hold on, I can do a little better than this. Tell you, this is Okay. And I'm okay, but it's, so here's y equals root x. Here's y equals 1. My region D is bounded below by the function y equals root x, above by the line y equals 1. But would this be right to put root x here and 1 here? Would that be correct? Why not, Ellie? Well, let's remind ourselves. Let's remind ourselves. Right, exactly. Let me just draw the picture a little bit bigger here. I'm just trying to do everything I can to make this as clear as possible, class. This is the kind of thing that would be easier in the classroom, right? But we're going to do the best we can here. I'm redrawing that picture above. If I do dx, dy, then I'm going this way, right? I'm going this way. So I'm going from the line x equals 0 to the parabola, not y equals root x, but x equals y squared. And so my limits here, my limits are going to have to be x equals 0 to x equals y squared. See that? And then the y limits are still 0 to 1. Does that make sense? Please let me know if you have any questions. Is everybody feeling good about that? Maybe give me a thumbs up if you're okay with that. Okay, good. Excellent, excellent. This problem is going to help you learn a lot. Malik, I trust that's a thumbs up, or did you mean thumbs up, or hold that thought. Okay, all right, all right. Well, I'll tell you what, let's look at another one. Let's look at another one while we're here, okay? All right, thank you, Malik, for your honesty. Appreciate that. Let's look at another one. What if we were to do, hold on. All right, this is all gonna be in the thing you copy. Let me go to another one here. Don't worry, you're gonna see this again. I'm just kind of having a discussion about this. Okay, so let's say we wanted to do dx d z dy. Okay, dx dz dy. Now that means that here Okay, here my first surface is going to be a function of what variables? So again, I gotta find a limit to put here, right? That's, well, x is going to be a function of y and z, right? That's correct, Malik. X is a function of y and z because you're using x. Tuna, is that okay? Okay. Let's look at the top here. Okay, on the top, that is going to be a U2 function of y and z as well. Okay. So now what we're doing is we're looking at this solid, okay, as well. The book, remember, we talked how solids could be treated as type 1 regions, type 2 regions, and type 3 regions. In this case, we're treating the solid as a type 3 region. So in other words, let me see, maybe I can, hold on here. Yeah. It isn't exactly perfect. Let me just see here. Hold on. I want to get some of this off here. Let's try it again. Okay, I want to draw this so it's parallel with the x-axis. So now you're going from a, well, actually, hold on. Let me, yeah, that'll work. So you're starting from a solid on the left until you reach a solid on the right. Okay? Now, a solid on the left going from a solid on the right. So when we did dz dy dx with dz, our beginning limits were from a surface. I'm sorry, I didn't say that right. For dz dy dx, we went from a surface on the bottom to a surface on the top. For dx dz dy, well, you know, the dx is really the key here. Because I'm doing dx first, I'm going to go from a surface on the left to a surface on the right, but I think I have this wrong. Hold on. I do have this wrong. Hold on. Let me do it again. Hold on. We're gonna get it, class. We're gonna get it. I mean, most of what I wrote was okay. All right, but let me just rewrite it again. So we're doing dx, dz, dy, right? Dx, dz, dy. Okay. So again, this was correct, what I wrote here. You have a function of y and z on the bottom, and another function of y and z on the top. But now your surface goes this way. Hold on here. Let me just, hold on, class. Right. So you're going from the back surface to the front surface. You're going from the back surface to the front surface. Because think about the x-axis. You're going in the direction of the x-axis. So you start off with the surface in the back, and you go to a surface in the front. What's the surface in the back of this solid? What's the surface in the back? What plane bounds the surface? I'm sorry. What surface in the back bounds this? What the solid is bounded by a surface in the back, and then the solid is bounded by a surface in the front along the x-axis. What surface is in the back? What plane is in the back? The YZ plane. That's right, Ellie. What's the equation of the YZ plane? The YZ plane, right, has equation x equals 0. X equals 0. So that's why we have a 0 here for the bottom limit. Now the limit in front, when we get to the front here, we're hitting what surface? What surface stops the solid from going any further along the x-axis? What surface is in the front? Give me the equation of the surface in the front. So the back, that's right, x equals y squared. So this is your y equals root x, or x equals y squared. So that's part of a parabolic cylinder. That's bounding the solid in the front. So the surface here is going to be x equals y squared. Okay, so far are we okay with that? Are there any questions on that? All right, but now what do we have to do? Now we have to project the solid into what plane to determine our region D? Okay, what do we project that solid in? We project that solid into what plane? Would it be the XY plane, the XZ plane, or the YZ plane? Well, look at your limits. Look at your variables that are left. You need to integrate with respect to Z and Y. So that's going to be the YZ plane. So if you project this solid into the YZ plane, okay, what's it going to look like? Pretend you're pushing the solid into the YZ plane, you know, and you want to know what the region looks like when you push the solid into the YZ plane. What's it going to look like? If you collapse a right triangle, that's right, Gnu. And in fact, it's going to look like this right triangle, right? That's what it's going to look like. Okay, so the limits here, you're going to have, you know, 1, 0, or I should say the 0, 1, and this is clearly the line z equals 1 minus y. Now, if you're doing dz dy, then you're doing this, right? So you're going from, hold on. You're going from the line z equals 0 to the line z equals 1 minus y, right? That's what you're doing. And so your z limits are going to go from 0 to 1 minus y. And then your y limits are going to go from 0 to 1. See how this works? Please let me know if you have any questions. So silence means you're all good with this. Silence on this means you're comfortable. If you're uncomfortable, let me know. Okay, Kino's good, all right. Malik's better, good, I like that. Ellie's good, Juliana's good. All right, well look, what's left to do here? What's left to do? What's left to do? You have to do dx, dy, dz. You have to do dy, dx, dz, and dy, dz, dx. Okay, you have three more orders to do. I want to give you about 5 minutes here to see if you can figure out the remaining the integrals for those remaining 3 orders. Okay. All right, and then I'm going to go to the solutions. All right, so take a few moments to think about that, and let's see what you come up with. Okay. All right, so say till 7:27. Let's just see what you can do. Okay. Okay, now I know you're still working on this. I'm just gonna, well, no, you got another couple minutes, so. All right, now let me start showing the solution here for at least the, here's the solution for, we did this already, okay? We did this already. So this is in the recording, and but I'll give you a moment in case you want to copy it formally for your notes. This is where we did the dz dy dx and dz dx dy. You notice how I'm always drawing pictures. Always drawing pictures, right? Helps. How many find pictures of regions, of drawing region D to be helpful when they do these kind of problems? Okay, Madeline agrees. And Ian agrees. Wonderful. Kino and Ellie. Okay, so here are some answers. Here's where we do the dx first. So I think we did dx dz dy, right? We did this one. Here's the answer for dx dy dz. And on the right, I've drawn the projections of the solid into the YZ plane. When you do dy dz, okay, dy means that you're, now it's like back to, well, you, go ahead, Matt, question? Okay, so I'm going from, y equals 0 to y equals 1 minus z. Now, z was equal to 1 minus y, right, in the problem. They had, the plane was z equals 1 minus y, but that means then y is equal to 1 minus z. Please let me know if you have any questions. And give me a thumbs up when you're good, and then we'll move to the two triple integrals where we do where we integrate with respect to y first. Okay. Good. Charles is good. Emma, Madeline, Ellie, wonderful. Gordon, okay, good. Juliana, good. And Kino, wonderful. Noah, how are you feeling with this? Yanu's good. So, okay. Malik's good, all right. Marwan, how about you? Marwan, you're feeling it? Study a bit more. Okay, thank you for your honesty. Okay. Okay, I like that. I like that. All right, well, let's go to the next ones. All right, and here it would be when you do dy first. So when you do dy first, let me just go to back to the picture here. This is such an important example. When you do dy first, you're integrating with respect to y. So you are looking then at a surface on the left to a surface on the right. In the direction of the y-axis. So you have a surface, starting surface on the left here, and an ending surface on the right. That encompasses that I don't want to say encompass, but those surfaces bound the solid in the y direction. Okay, so the surface on the left is y equals root x. The surface on the right is y, well, this is the surface on the right, but we would write that as y equals 1 minus c. And then if you project this solid into the xz plane, you're going to get a parabola. You're going to get a parabola. And this is the scenario then that you're looking at. So there's y equals square root of x, y equals 1 minus z. And then if you're doing dx dz, okay, dx here is horizontal, dz is vertical. And that is I want to say this the right way. Hold on here, everybody. So that I want to just comment on one thing here. you know, how, like, so like this right here, this parabola here, okay, which would form the boundary of our region in the XZ plane, that is the intersection of y equals square root of x and z equals 1 minus y, right? That's the intersection of those two surfaces. So that means we could replace the root y here, okay, this root y, with the y equals root x, because we are limiting, the boundary of our region is this intersection between those two surfaces. So that's why you can say z equals 1 minus root x or x equals 1 minus z squared. Absolutely amazing. And then, of course, if you do dy dz dx, you're going to get the triple integral that you see here. So you see, this is a very good exercise, because if you can do this exercise, you are very, you know, you have a good comfort level with finding limits for triple integrals. Even if you use MATLAB to help you determine the value of a triple integral, you still need to find the limits, right? And on the exam, which is going to be posted next Monday, it'll be, by the way, after class. We'll need all of our class next Monday. But the exam will be posted after class. You know, naturally, I want to see work on the triple integrals, but you can always use MATLAB to help verify your answers. And we're trying to keep our triple integrals, you know, you can get very complicated, right? But, you know, we're just trying to keep things comfortable here, okay? Okay, are there any questions on this before we move on? I know these problems take time, you know, so you notice the assignments, I try to make them reasonable because they do take time. I'll mention here, it says here that I got a message just from the MindTap that has the ebook, says they're going to have maintenance on Wednesday, July 21st from 5 to 5:30. Oh, that's in the morning, 5 to 5:30 a.m. Okay, so, but it says you might, if you, well, you'll see the message, okay? All right, let me just, I want to bring up this 12.7. How many felt this example was helpful? Was this a helpful example? You feel a little better about triple integrals? Excellent, excellent. Okay, wonderful, wonderful. Okay, let me bring up the ebook. Okay, so you see here, they want to do a triple integral over a tetrahedron. and tetrahedrons bounded by those 4 planes. And I want to really, I mean, you've had some experience doing this kind of these kind of problems. I want to go right to where they have the answer. Okay. One moment. Okay, so we can actually, so like I'm thinking, okay, you know, you're on an exam, you're working through a problem, triple integral problem, you're doing your work, you get an answer, and you like to be able to check to see if your answer is correct. Can you use MATLAB? Can you use MATLAB? Well, I've written a little piece of MATLAB code that shows you how to do a triple integral for this particular example 2 from section 12.7. And you can see that the z limits, looking at the top there, in the highlighted in the blown up box in the box there, z limits go from 0 to 1 minus x minus y. The y limits go from 0 to 1 minus x, and the x limits go from 0 to 1. So let's go ahead and see how this would be done in using MATLAB. So for that, let me bring up the okay. So here, wait, hold on. What did I bring up here? Hold on, I don't want to bring that up. I'm going to bring up the Blackboard. So Blackboard. Here we go. Can everybody see Blackboard okay? Okay, good, good. There's that announcement I sent about your MATLAB assignments. Okay, very good. So if you go to, in Blackboard, go to MATLAB Programs. Click here to see the MATLAB programs. 12.7, section 12.7. There's a MATLAB program for triple integrals. Okay, and this program will demonstrate how to compute a triple integral using rectangular coordinates. So on that note then, I'd like you to open up that program. Okay, go into your MATLAB. Now the answer for this example was 1/24th. Okay, for this example 2. Okay. Hold on here, one moment. Okay, let me make this visible to you. Okay, so here's the program. And, you know, MATLAB always has, every year they have additional ways to do things. For instance, how to represent functions and so forth. But I like this way of doing triple integrals. This is, to me, makes the most sense. So you have 3 nested integrals here. INT stands for integral. The first integral, the first nesting, is the integral. Okay, so what's this mean here? It means, all right, for the function, where the function f equals z, hold on here, which is our function f equals z. Z is the integrand, okay? So we're going to, well, I want to say it's the right way. The function that the function inside the triple integral, the function of x, y, and z, is now wait, is the function equals z. So in other words, let me go back to the book again, so you can see this. Okay, so there is our triple integral. So f of x, y, z is equal to z. And the z limits go from 0 to 1 minus x minus y. So if we go then to our code here, we're going to integrate the function. And in line 4, it tells you the function equals z. We're integrating it with respect to z, and the limits go from 0 to 1 minus x minus y. Now, what that's going to do is it's going to give you an integral with respect to, well, it's when you do that, you're going to get a double integral with respect to x and y. Okay, that's how MATLAB's going to store that. Well, all right, now you're going to take that double, you got that double integral. Now you're going to, like the outer integral, say, you're going to integrate with respect to y. Okay, you're going to integrate with respect to y. And so that goes with this integral, and y goes from 0 to 1 minus x. Do you see that? Okay, and then finally, the last integral, okay, in your triple integral, the last integral here, x goes from 0 to 1. So you see, that's how you write it. And let's just and you notice in the second line there's a thing called clear vars. What clear vars? And then you have to, of course, in the third line, define your symmetric variables, symbolic variables, I should say, x, y, and z. But line 2, clear vars, just clears all the variables in your workspace. Okay, so that you're starting fresh. Because how many of you use MATLAB and maybe occasionally have gotten the wrong answer, maybe in another class, because an older variable is stored in there and it's interfering with the current variable? Has anybody ever had that experience with MATLAB? Well, Charles says all the time. Okay, well, clear vars, it will help fix that problem. So that's why traditionally when you write your code, you want to have clear vars there to start with. That being said, let me go ahead and, one moment, copy and paste that in the command line. Hit enter, and you get 1/24. And that is the answer. Okay, so see, when you work a triple integral out when you work it out and show all your steps and you get your final answer, you can check your answer in MATLAB. Okay. Let me see, there was a chat thing here. Okay, Charles. Oh, okay. So Charles got got something very different in imaging. Is this for where you work, Charles? You use MATLAB to get a heart image, and you got a brain image instead. Was this like at your place of work? Okay. Where do you? May I ask where you work, Charles? Is it NIH or where do you work? NIH. Okay. Creating synthetic magnetic resonance images, right? Wonderful. Okay. Okay. And is MATLAB being used there, Charles, in the coding? Okay, there you go. So, hey, this is state-of-the-art stuff. Excellent. Thank you. Thank you. All right. Are there any questions on this? How many did get this answer, ran the code, and it worked for them? Obviously, for different problems, you change the code, right? But did anybody try the code out? And, yes, got it. Okay, good, Marwan. Excellent. Good, Ellie. Okay, I'm going to stop here.